All right, so we're in chapter 10 now, and in chapter 10 we are covering what are called counting problems. Counting problems occur in a number of areas throughout mathematics. They're really important in probability theory, which is something you learn about in a statistics class. The idea behind a counting problem is trying to count the total number of objects or occurrences of a particular event. In some kind of application problem. Now, initially, when people first start learning about counting problems, oftentimes the question arises, well, why are we talking about this? I know how to count, right? That's like the first thing I learned how to do mathematically, is count. But the reason for this is because a lot of things are not as straightforward to count by simply enumerating them one by one. An example of something that is that simple is trying to determine the total number of possibilities when rolling a single standard die one time. Standard die has 6 sides, and you roll it, and you can have a total of 6 possibilities. 1, 2, 3, 4, 5, or 6. There's only 6 possibilities there. That's your total. Now that's something that we call a one-part task, because you're only rolling that die a single time. Those are the easiest things to count, because you're really just looking for the total number of possibilities of one occurrence of that event. But most of the counting problems that we look at that are kind of more interesting involve what are called multi-part tasks. 2-part, 3-part, 4-part, whatever number of parts. An example of a 2-part task is similar to the one we just talked about. If you take a standard 6-sided die and roll it 2 times, one after the other, and then if you try to count the total number of possibilities of the numbers that turn up in those 2 die rolls, that's not as straightforward to count the way that we count in the case of a one-part task, because you're looking at combinations of results now, not just a single list of results. So this is where we get into the need for what we call systematic counting. Or in this section where in particular we're looking at systematic listing. Finding a way to represent all the possibilities in a way that you know that you've accounted for everything. So we're actually going to make that our first example. Suppose we roll a standard die twice, once after the other. We want to determine the total number of possible results. Now, a little bit later, I believe in actually section 10.2, we're going to develop a mathematical rule for dealing with multi-part tasks. But for now, we want to look at just listing everything in an intelligent way. So what I'm going to do is I'm going to create a table to do this. Now, the first roll of this die we know has 6 possible states. 1, 2, 3, 4, 5, 6. Those are the 6 possibilities, let's say. Okay, and then the second roll has a total of, again, 6 possible states. 1, 2, 3, 4, 5, and 6. So this column right here, this is going to represent my first roll of that die, and up here this will represent the second roll. Okay, and now what I'm going to do is use these to create this table here. I'm going to go like this. And then I'm going to create some columns like this. And what I'm going to do is fill in this table with the different possible results. So for example, if my first roll was a 1 and my second roll was a 1, that's represented by this cell of my table right here. And I'm going to write that in the form of an ordered pair, where the first number represents the result of the first roll, second number represents the result of the second roll. So this row right here is going to be all the possible results of these 2 die rolls if the first roll is a 1. Notice this would be 1, 2, 1, 3, 1, 4, 1, 5, and 1, 6. Okay, and then I can move on to the second row. What does that row represent? This is a listing of all the possible results if my first roll is a 2. So I can say 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, and 2, 6. And you notice this is just a matter of filling in all the ordered pairs that we would consider our possible results here. So 3, 5, 3, 6. Now this is something that you do in a probability theory or a statistics class like I mentioned before. And if you've been through statistics, you've seen this done before. I guarantee it, because this is a very standard probability example, rolling die, and what we do in probability theory is we consider the probability or the likelihood of different events occurring. So for example, if you're rolling 2 die, you could look at the total number of possible combinations like we are here. You might be interested in other kind of more interesting events though. You might be interested in the total number of ways that you can roll 2 die such that the sum of the two numbers is an even number or something like that. That's a possible event. And by listing all of these ordered pairs like this, it gives you what we call an exhaustive list of possibilities. That's a 5. And you can find those. Like, so for example, if I'm looking for the total number of possibilities where the 2 die rolls add up to an even number, I can actually look at the numbers here and add them up in my head. 1 plus 1 is 2. That's an even number. I would count that possibility. 1 plus 2 is 3. That's an odd number. That would not be counted if I'm looking only for even sums. But we're not really looking for that here. Here we're just looking for the total number of possible results. I could count these one by one, 1, 2, 3, 4, 5, 6, and so on. Or I could recognize that this forms a nice square grid, a 6 by 6 grid. The total number of possibilities then, thinking of that as like a geometric area problem, is 6 times 6, or 36 different possible results. Now, it's important to note in a case like this becomes more important in later sections, that we are considering, for example, 2, 1 to be a different result than 1, 2. If I rolled both die at the same time and one comes up as a 1 and the other one comes up as a 2, I might not make that distinction. But because this number right here represents the result of my first roll, and this represents the result of my second roll, the sequence is different in both of these, so we count them as different results. Okay? The next example is kind of a follow-up of what we just did. So consider the experiment that we just did in the previous example up here. How many possible results exist in which the first and second die rolls are different? In other words, if you're rolling one die after the other, there is the possibility that both rolls give me the same number, right? So a 1, 1 or a 2, 2 or so on. We want to look at all of the other possibilities. How many different possibilities are there in which both numbers are different? Now, one way to do that is to go through and just look for all of the ordered pairs where both numbers are different and then count those. But if you notice, that makes up the majority of those numbers, and we're trying to do this in a systematic way, a more intelligent way that's efficient. There's far less combinations where both numbers are the same. In fact, they're aligned in a very convenient way along this diagonal here. 1, 1, 2, 2, 3, 3, and so forth. You'll see 6 combinations where both numbers are the same. So if we want the total number of combinations where both numbers are different, we could take the total, 36, and subtract the total number, or subtract the number of combinations in which both rolls were the same, giving me a total of 30. That's better than counting 30 individual possibilities. It's more efficient, okay? So you want to use techniques like that. That's kind of the idea behind this systematic approach that we're taking. Okay, let's move away from the dice example and let's consider something different. In this example, it says that we have a total of 5 different candidates being considered for a committee consisting of 2 people. There's lots and lots of problems in this chapter where we talk about choosing committees. It's kind of a nice counting problem. How many such committees can be assembled from these 5 candidates? So oftentimes when you're trying to choose people or objects that aren't necessarily named, it's nice to give them some kind of symbolic representation. So we're talking about 5 people, 5 candidates. I'm going to assign them letter names, A, B, C, D, and E. These are going to be the symbols that I use to notate these people. It's easier to write than writing a bunch of long names. Now, we had to think of this as like a pool, a pool of people that we're choosing from, but we can only pick 2 to belong to a committee. And we want to know how many possible committees can be formed from these 5 people, considering the fact that a committee in this case consists of only 2 people total. So for example, let's start, again, systematic, that's the idea. Let's start by thinking about the total number of committees that we can form in which person A is one of those candidates that are chosen. I can list them here. So A, B, that's the committee consisting of person A and person B. If I'm keeping person A on the committee but looking at the other possibilities, I would have AC, AD, and AE. Those are all the possible 2-person committees that I could choose from these 5 candidates, where A is one of those candidates. Okay. Now let's think of all the possible committees where person B is chosen. Now, if you think about the previous example where we did the 2 die rolls, you might think of listing BA as a possible committee. But in the case of a committee, it's not important who was chosen first and who was chosen second. If I choose person A first, followed by person B, that results in the exact same committee as if I chose person B first, followed by person A. So AB and BA are not considered distinct here. It's the same thing. So I wouldn't count that. In fact, if BA is not a choice, I also can't choose BB because the same person can't be chosen twice. So BC is the first combination that I would look at, followed by BD and BE. Okay, those are all of the possible committees that can be chosen where person B is one of the candidates who were chosen. BC, BD, BE, and then we already chose AB. Those are all 4 possible cases. Now let's look at all the cases where person C is chosen. Notice person C has already been considered for a couple of committees here. So I'm not going to do CA, since that's no different than this. I'm not going to do CB, that's no different than BC. CC doesn't make any sense, so CD and CE are the only 2 possible committees I could choose. Finally, let's consider person D. How many different committees can person D be considered for? Well, we've already considered DA, DB, DC, DD doesn't make any sense, so DE is the only one that we haven't accounted for yet. Now notice I don't need to make a 5th column here for the total number of committees consisting of person E with one of the others, because there's only 4 choices to pair up with person E, and we've already considered all 4 of them in this diagonal right here. So this accounts for all possible committees, and I approached it in a systematic way. I found 4 people here, 4 committees here, 3 additional committees there, 2 committees up there, 1 committee there. This adds up to 10. There's a total number of 10 2-person committees I could create from a pool of 5 candidates. Okay. Later on in this chapter, we're actually going to talk about something called permutations and combinations. And this is an example of a combination problem where we're going to derive a formula that does this for you without the need for any listing at all. But we're kind of working our way up to that point. Okay, let's take a look at another counting example. In this case, we're looking at a lock that has a 3-digit code, and it's a very specific 3 digits. So we have this criteria that the code has to conform to. The first digit of the code has to consist of a number from the set 1, 2, 3, or 4. The second digit is not a number at all. It's one of 2 possible letters, A or B. And then the third digit has to be one of the numbers 7, 8, or 9. And what we're trying to do here is determine the total number of possible codes that we could come up with that fit this criteria. We're going to use a different approach this time. I could use this listing approach that I did here, and it would work, but notice we are choosing digits from different sets here. So it would look a little bit different than this, where the 2 candidates were being chosen from the same set. We're going to use an approach we haven't talked about yet called creating a tree diagram. So here's the idea of a tree diagram. We're going to have 3 stages of this code writing process. a stage for the first digit. We have to choose a first digit. We're going to have to choose a second digit. And we're going to have to choose a third digit. Okay? Now we know the possibilities for the first digit, numbers 1 through 4. So I'm going to list them underneath this thing here. 1, 2, 3, 4. Okay? And now each of these first digits, these possibilities for my first digit of my code, can be followed by a second digit fitting this criteria. So if my first digit is a 1, there are now 2 branching paths as to what the second digit could be. They could be either an A or a B. So I create those by actually writing those paths as like branches in a tree. The second digit could be an A or it could be a B. Same possibilities here. If my first digit is a 2, the second digit can be either an A or a B. And if my first digit is a 3, 2 possibilities from there are a second digit of A or B, and then similarly down here. Okay, this is 4 groups of 2 so far. That's 8 possibilities for the first and second digits of my code. 1A, 1B, 2A, 2B, 3A, 3B, 4A, 4B. Now we need to consider the third digit. And this is where I always get cluttered in how I write this. So the third digit can be one of 3 different numbers, 7, 8, or 9. So if my first 2 digits are 1 and A, that branches into 3 different paths from here. 7, 8, or 9. Same thing with B. 7, 8, or 9. So this accounts for 6 possible codes where all 3 criterion are met. 1A7, that's a possible code. 1A8, that's a possible code. 1A9, and so on. And I'm going to do this for all of the others. So this A here can branch off into 3 different paths, 7, 8, or 9. Here, 7, 8, or 9, and yes, it does get very cluttered. You have to kind of think ahead as far as how to leave yourself space in these tree diagrams. I have 7, 8, or 9 here. 7, 8, or 9, and then here. Okay. By the end of this, I have a whole bunch of different possible codes. Again, this first path here, going from 1 up to this 7 right here, is the code 1A7. That would represent 1A7. And then this code right here, 1A8, is another possible code. I'm not going to list every single one of these, but if you notice, if I just count all of the entries in this column, each one of those is going to correspond to one of the possible codes. So I could count the total number of possibilities by counting how many numbers appear in this big column right here. It's a lot of counting. It's not that bad, but let's take a more systematic approach again. Remember before, when we looked at this second column, I said that there were 4 groups of 2 appearing here. 4 groups of 2 letters, A, B, A, B, A, B, A, B. That amounts to 8 possibilities. Each one of those branches off into a group of 3. 8 groups of 3 appearing here. You can see those groups if I circle them like this. 1, 2, 3, 4, 5, 6, 7, 8. 8 groups of 3. So, off screen a little bit there. From here, rather than count them individually, I could just do 8 times 3, which is 24 codes possible. Okay, and again, that's a systematic approach. These tree diagrams are cumbersome. They create a good visual, but they're cumbersome to draw, and again, it's because of these kind of space restrictions that we have. So again, in the next section, we're going to find a way to come up with a very, very simple formula that does this without the need for sketching out all of this stuff. Okay? All right. So what we've been looking at primarily are these things that we call multi-part tasks, which we've talked about and defined that already. But you can kind of categorize multi-part tasks oftentimes into one of two categories, something that we call with replacement and something that we call without replacement. So again, a multi-part task is when you are doing a task in stages. So for example, when we were choosing that code in the previous example, that consisted of 3 parts or 3 stages. We picked a first digit, and then once we chose that first digit, we considered all the possibilities for the second digit, and then we considered all the possibilities for the third digit. 3 stages or 3 parts. Now, if I were allowing myself in a multi-part task where I'm doing the same thing every time, so let's consider an example where we're rolling die. If I roll a die and I get a 1 for my first roll, then if it's possible to get a 1 on my second roll, we call that with replacement. So that's a multi-part task with replacement. If it's not possible to get the same result more than once, we call that without replacement. And this next example kind of illustrates why we would call it that. So let's consider a case where we have a bag consisting of 3 balls, each of a different color, red, blue, and green. You're going to reach into the bag and you're going to pull 1 ball out. And then you're going to reach in and pull another one out. There's 2 different ways to go about this experiment. One is called with replacement. So what that means is that if you reach into the bag and you pull out, let's just say, the green ball. With replacement would be putting the green ball back in the bag and then drawing a second one, because that creates the possibility that the green ball can be chosen a second time. You've replaced that ball in the bag, and we call that with replacement. On the other hand, if you reach in the bag and you pull the green ball out and you set it aside, and then you reach in and pick out one of the remaining 2 balls, that's called without replacement, because you didn't put the green ball back that time. These 2 different ways of thinking about this experiment give us different answers to this question. Okay, so let's look at this again. A bag contains 3 balls. 1 is red, 1 is blue, 1 is green, and we want to look at the total number of ways to draw 2 balls, one after the other, with replacement and without replacement. So let's think about with replacement for a second. I'm going to do this similar to how we did the committee example. Okay, so for part A, let's say that the first ball we chose was red. I'm going to call that R. If it's with replacement, then I'm putting the red ball back in the bag, which means the red one can be chosen again. So RR is a total possibility, or is a possibility for this experiment with replacement. I could choose red and then blue, and I could choose red followed by green. These are the 3 possible cases where the first choice is a red. Okay, what about if I choose blue first? Blue, red. Now, I am considering BR to be different from RB in this case because we are paying attention to what the first ball was and what the second ball was. And if the first ball over here is red and the first ball over here is blue, those are not the same first choice. So we consider these combinations different. Okay, blue, red is a possibility. Blue, blue is a possibility because, again, we're considering replacement. We can choose the same thing twice. Blue, green is a possibility as well. Finally, if I look at all of the possible combinations of choices here, where green is my first choice, I could get green red, I could get green blue, and I could get green green because it's with replacement. That's a total of 9 possibilities. Okay? For part B, we're looking at without replacement. What's the difference between with replacement and without replacement? Well, if we're not using replacement, that means that we're not putting the ball back in the bag, which consequently means that it's impossible in this case to choose the same color twice in a row. What that does is that eliminates 3 of the possibilities that we looked at from this list. We cannot get red red, we cannot get blue blue, and we cannot get green green, but we can get the other possibilities. So if there were 9 possibilities before, and we're removing 3 of those because we're doing without replacement, that means now there are only 6 possibilities. Okay, so I'm not going to create a brand new list. I'm just going to use the one that I already came up with in part A. All right, last question. There's a few problems in the homework that deal with this, where it's a little bit more visual. So in this case, it says we're looking for the total number of squares in this image below. Now, sometimes people will look at this and they'll say, oh, there's 16. I see a 4x4 grid of squares. But you'll notice it didn't say anything about the size of the squares that can appear in this image. So yes, there are 16 of these small squares here. But notice, if I look at a 2x2 little grid within this larger grid, that forms a square as well. I can also form 3x3 squares, and I have a single 4x4 square appearing in the whole thing. So again, I don't want to just count these one by one. I want to think about a systematic way of doing this. So there's different ways to approach this, but one way is to use corners. Your book uses this in a kind of a different method. If you look at the example in the book, there's a case where they're looking for the total number of triangles, and what they do is they label all of the vertices in those in that grid that they give you, and then have you write out all the possible triangles as sequences of 3 letters at a time, which is a great approach. I'm not going to use that approach here though. Notice if we're looking at a square, one thing we know for certain is that there has to be a top left corner of that square. So let's first consider all of the 1x1 squares. How many 1x1 squares are there? Well, yeah, I can count them directly. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I can very clearly see there are 16. But let's consider the systematic approach for a second. I'm going to go through and circle all of the top left corners of the 1x1 square. So I have 1 here, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, notice when I'm looking at those, I'm looking at corners of these little 1x1 squares, and some of the corners here I did not circle because they can't be in the top left of any of those. These are all of the top left corners. Okay, now let's look at the 2x2 squares. Well, to show you an example of a 2x2 square, this guy right here is a 2x2 square, right? So notice its top left corner is up here. So here's a question. Can any of these guys down here be the top left corner of a 2x2 square? And the answer is no, because for example, if this one was the top corner of a 2x2 square, then the top left corner specifically, then the 2x2 square would have to extend beyond the picture here so that it has the correct dimensions. We don't have enough squares down here to create that 2x2. So considering that, if I want to count the total number of 2x2 squares in this grid, I can eliminate not just that top left corner, but these 4 top left corners, because all of them suffer from the same problem, right? Now notice this column of corners right here, can these circles represent the top left corner of a 2x2 square in this grid? And no, none of them can, because for example, if this was one of the top left corners, because it's the top left, the rest of the square would have to extend to the right of it. And I have 2 squares here, but I'm missing the 2 squares that would have to be over here to complete that 2x2 square. So that means that this, and this cannot be the top left corner of any 2x2 squares in this grid. All of the remaining, though, circled corners can be the top left corner of a 2x2 square in this grid. And you can confirm that pretty easily. Here's one of them where I drew it, but for example, this circle right here creates this 2x2 square. This circle up here corresponds to this 2x2 square. You can confirm it for all of them. So what have I done here? I've eliminated several of the possibilities, and I've now got 3x3, like a 3x3 grid of these circles remaining. That means there's 9 possibilities for the 2x2 case. What about 3x3 squares? Well, here's an example of a 3x3 square right here. Okay. Can I do something similar? Can I eliminate some of the remaining circles? Now notice the ones that have already been eliminated. If this cannot be the top left corner of a 2 by 2 square, and then it certainly cannot be the top left corner of a 3 by 3 square, because that would extend even further into this region that doesn't consist of any squares. So let's just look at what remains. Can this be the top left corner of a 3 by 3 square? No, because again, even though it determines a 2 by 2 square right here, 3 by 3 takes me beyond the dimensions of this figure. And by a similar reasoning, you can actually rule out all of those. You can also rule out those guys. Hopefully you can see why. So none of those can be the top left corner of a 3 by 3 square, but these 4 can. And again, that's easy to verify. Finally, we know that there's only one 4 by 4 square in this entire grid. It's the whole thing. And this would be its top left corner. So we can eliminate these 3, giving me one possibility for a 4 by 4 square. I can get the total number of squares now by adding all of these results. 16 plus 9 plus 4 plus 1, that adds up to 30. There's a total number of 30 squares in this example. Okay? So that's a little bit on systematic listing. Like I said, well, for one thing, there's plenty more examples that we can come up with, but this gives you some tools for handling these types of problems. Starting in section 10.2, we're going to be developing some formulas and much more efficient tools at doing this that prevents us from having to do so much listing.